So hello and welcome to this tutorial on drawing electron configurations and orbital box diagrams. There's not really a question that I'm going to be taking a look at here. Rather, I'm just going to be taking a look at some known issues that students generally tend to have when they first start drawing these types of representations. So if you have started writing electron configurations and orbital box diagrams, you might have come across a number of elements that don't appear to abide by the Aufbau Principle. That is, you have filled in the appropriate electron configuration by the way that the electrons should fill based on the available energy levels, but yet when you go to look at the actual electron configuration, you find that it looks a little bit different. And the reality is, once we get to the third and fourth periods and beyond in the periodic table, there are a number of elements that actually do violate the Aufbau Principle. Now, the question might be, well, why do they do that? And the best answer that I have for you is because that's what they do. Now, I'm not going to ask you to remember every single one of those, but the common ones that I often ask my students to know are these 5 in no particular order. They are copper, silver, and gold, and you will notice that those are in the same group, and effectively they will have kind of the same sort of exception. And the other 2 that I often ask my students to know are chromium and molybdenum, and again you will notice that those 2 are also in the same group. Curiously, tungsten, which is just below them in the group, actually does abide by the Aufbau Principle. But anyway, those are the 5 that I normally ask the students to know. So I'm going to take a look at one right here. And the first thing that I want you to just sort of review very quickly are the different versions of electron configurations and orbital box diagrams that can be drawn. You will notice that at the top here I have 2 full electron configurations. So with my students I refer to these as electron configurations, and you can see that they give us the sublevel that these electrons are found in, they give us the orbital, and they tell us the number of electrons that are found in that particular sublevel. So the top one that I have here, this expected electron configuration, would be the electron configuration of copper if it abided by the Aufbau Principle. But this is not actually what is observed. The actual observed electron configuration of copper sees 1 electron in the S and 10 electrons in the D. Now what you will notice is that this leaves us with a half-filled orbital in the S, because the 4s orbital can contain 2 electrons, and it leaves us with 5 fully filled orbitals in the 3d sublevel. So the belief is that having a half-filled 4s and a fully filled 3d is more stable than a fully filled 4s and a partially filled 3d. Now again, that is a theory. What we have to understand is that not all elements will abide by this. The reality is this is just the electron configuration of copper. And just because we might be able to predict that other elements should be more stable with a particular electron configuration, that does not mean they are. So you might be able to visualize this theory of ours a little bit better if I fill in the condensed orbital box diagram for copper. And again, what you'll notice is that we have a half-filled 4s sublevel, and we have a fully filled 3d sublevel. Now finally, if we take a look down at the full or complete electron configuration for copper, we can see that the actual full electron configuration for copper would look like this. Now the reason that I've put the full electron configuration down here is because students often have a tough time discerning between the various terms that are used or involved when we start talking about orbitals and sublevels and energy levels and principal quantum numbers and so on and so forth. If we take a look at this particular representation of copper, that can help us address all of those things. So if we want to take a look at how many sublevels we have, I have grouped each of these into a sublevel. So there are 1, 2, 3, 4, 5, 6, 7 sublevels here. If we want to take a look at how many energy levels we're talking about, or if we are asked for the principal quantum number, that's the number that precedes the letter representing the block on the periodic table, or the orbital shape, if you like. So if we take a look at this, we have 1 energy level, we have 2 energy levels, we have 3 energy levels, and we have 4 energy levels. Each of these represented by a different principal quantum number. So we have 1, 2, 3, and 4 in this case. So if we want to take a look at how many of the sublevels are represented by the third principal quantum number, or the third energy level, all we have to do is take a look at the sublevels that have 3 in front of the letters. So in this case, we have a 3s, we have a 3p, and we have a 3d. Now, if we're asked to figure out the number of electron-containing orbitals, you will notice that every single one of these orbitals, and remember, each orbital is represented by a box, every single one of these orbitals contains electrons. So if we're asked for the number of electron-containing orbitals, we just count the orbitals, or the squares, that contain electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 electron-containing orbitals. 14 of those orbitals are fully filled, and one of those orbitals is partially filled. So if you are asked a question with regard to orbitals, sublevels, principal quantum numbers, or energy levels, just remember to draw out the full orbital box diagram, and it will help you be able to visualize that question and that element a little bit easier. So the last thing I want to talk about for now anyway, with regard to electron configurations, is when we start talking about excited and ground state. So if you take a look here, you will see that this is the ground state of a noble gas, of neon. And we can see that all of neon's 10 electrons are accounted for. 2 in the 1s, 2 in the 2s, and 6 in the 2p. Now, this is what we refer to as the ground state. All of the electrons are in the lowest available energy levels. They are in the lowest available sublevels. They are in the lowest available orbitals. You can think about this like parking at the mall. All of the closest spots are taken. If any more electrons want to get in here, they have to go to the next available parking space. And so in that way, they fill, using the Aufbau principle, in the lowest energy orbitals available. Now, if we have something that is excited, if one of these electrons are excited, they're going to absorb a certain wavelength of energy, a certain amount of energy. We refer to this energy as a quantum. When it absorbs this quantum of energy, this packet of a specific amount of energy, it moves up to a higher energy orbital. We say that it jumps. In actuality, it doesn't jump or move anywhere because there's no transition between orbitals. It just changes its probability distribution. If we want to talk about it another way, we say that that orbital would change its shape. So if we are then going to draw something that is excited, all that means is one of these electrons are going to move to a higher available orbital. Now, it could move theoretically to any orbital because it could absorb any quanta or any amount of energy. But for simplicity's sake, and the way that the textbook does it, if we are going to draw something excited, we are just going to move it up to the next available orbital. So, if I'm going to draw an excited version of neon, I'm going to take one of the outermost electrons from the 2p, just one of them at this point, and I'm going to move it up to the next available orbital. And the next available orbital is in the next energy level. It is in the 3s. So you can see now that I have the same number of electrons. 2 plus 2 plus 5 plus 1 is 10. But you will notice that the 2p sublevel is not full. One of its electrons has moved from one of the orbitals into the neighboring 3s orbital, a higher energy orbital. So in some respects, we say that it has jumped to a higher energy orbital. Now, it has absorbed a certain wavelength of light to do that, and when it jumps back down, it's going to re-emit that light. So this is one of the many excited electron configurations for neon. And every other element is going to go through the same process of being excited by different quanta of energy, and that's how we get the various absorption and emission spectrum for the different elements. In summary, if you are asked to establish or determine whether or not an electron configuration is excited, you have to take a look at what the ground state electron configuration is for that element. Typically, we fill it up using the Aufbau principle, unless of course we have an exception, and we see if one or more of the electrons appears to be in a higher energy orbital than we would expect based on our ground state electron configuration. And in turn, if you're asked to come up with an electron configuration for an element that has been excited, then you can take one of the electrons from the highest sublevel and move it to the next available sublevel. So hopefully this tutorial has helped a little bit with some of the stumbling blocks that students come across when they first start doing orbital box diagrams and electron configurations. That is, exceptions to the Aufbau principle, the different types of electron configurations and orbital box diagrams that we can draw, and excited and ground state electron configurations. Now in future tutorials we're going to talk about multivalent elements and how electrons move and how we can display or demonstrate ionic bonding, but that's for another tutorial. Thanks for watching.